for joining us for today's webinar. Just a little housekeeping before we get started. This webinar is being recorded. All attendees will be in listen-only mode. We'll open the floor for discussion during the Q&A portion of the presentation. You can also type your questions into the chat box. I'd first like to introduce our Director of Marketing, Renee, who will talk a little bit about our company and will introduce Barry. With that, I'll hand it over to you, Renee.
All right, thanks, Laura. And hey, everyone, I hope everybody's doing good today. You're staying healthy and you're safe. I just want to take a quick minute, give you a little bit of a background on who we are at CDI Engineering Solutions. So we provide critical engineering, design, architecture, and project support services to companies and organizations in energy, chemicals, and infrastructure sectors. Next slide, Steve, or Barry. So as you can see on this chart, on this map here, we're a team of about 600 people, and we've got 10 offices across Texas, Louisiana, West Virginia, Michigan, and Pennsylvania. Next slide. So we provide many services and capabilities, and as you can see on this slide, electrical and power systems, instrumentation and control, process engineering, civil, aviation infrastructure, etc. And I just wanted to let everybody know that if you have any questions after the webinar or you need help in any of these areas, we would be very happy to help you. You can give us a call, you can check out our website, or follow us on social media for more information and just to see what we're up to. So next slide, please. So this is Barry Thrasher. We're very lucky to have great talent across this entire company. And today I'd like to introduce Barry to you. He's a very long tenured and very talented engineer. He's got over 30 years of experience in the technical leadership roles and mechanical engineering at manufacturing and production sites. Those include upstream, midstream, and downstream oil and gas, and chemical, petrochemical facilities, including catalysts. He's been a subject matter expert at numerous sites and locations, not just domestically, but also internationally. And Barry's led efforts on analysis and mitigation of complex mechanical induced vibration, flow induced vibrations, and acoustical induced vibrations throughout his entire career. And that's actually what he's here to talk about today. So without further ado, Barry, I'll hand it over to you, sir.
Okay, thank you, Renee. Very nice introduction. Sound check, everyone hear me okay?
Yep.
Yes.
Perfect. Okay. So a little housekeeping. Let me get my, okay. So agenda, we're going to do a quick safety topic, and then we're going to go into the presentation, evaluation, mitigation of vibration-induced dynamic stresses, which is really what everyone's here to talk about. But I do want to cover safety first. So the safety topic that I have here for today is the 6 tips of driving safely. This holiday seasons with the loss or injury of loved ones is a bad thing. So we want to do everything we can to bring this to everyone's, forefront on safety. And so I want to point this out to everyone. So the 6 tips I want to present are: first, plan ahead, before you start your trip. Make sure the vehicle's in good shape, do the walk around, check the tire pressures. As the winter comes, tire pressures tend to dwindle and become lower than they should be. So check them. And if you're going somewhere where it's going to be unusually colder than it is here where we normally live, you need to consider a cold weather pack and so forth, ice scraper, things to that nature. The next thing I want to point out is stay fresh and alert. Make sure you're well rested before a long drive. And I mentioned this study here that was conducted by the NHTSA that basically says that there's a lot of crashes, a lot of people get injured and hurt, and even death that occurs from driver fatigue. So this time of the year, everybody's busy trying to get Christmas together, and if you get to the end of the day and you really need to drive somewhere and you don't think you're fresh enough, don't go. Wait until the next morning. So mind your speed. Give everybody plenty of time and to stop and react, because this everyone's in a hurry. It's a holiday season, and I mean, getting there 5 minutes later is not going to change the holiday. Having an accident and not getting there does change everything horribly bad. So mind your speed. Everyone really needs to think about driving defensively, also, even dealing with the weather, but also dealing with aggressive drivers. There again, it's not going to be any real issue if you're 5 or 10 minutes late. So just drive defensively. It's a holiday. Take the holiday off and enjoy your time off and relax, and don't rush yourself. Don't get in a hurry. Another one, don't drive impaired. We're probably many of us will be out, and maybe opportunity to actually indulge in an adult beverage somewhere. So, please be cognizant of that during the holiday season, and know your limit there. And that's very important. And then holidays are a time for distraction. So please think through distractions and understand that, okay, I'm fixing to get behind the wheel of this car, and I need to focus on the wheel of this car and this road, and not what such and such got such and such for Christmas, and I don't need to be texting them while I'm trying to drive, so avoid those distractions. They're really easy to do, especially during the holiday season. So that's really my safety topic that I wanted to present. So y'all all be safe and have a good holiday. And we'll see everyone after the first of the year. So without any ado, we get into the evaluations and mitigations of vibration-induced stresses. So basic agenda for this discussion is, some basic information focus. We're going to go over a few key definitions that'll help. But the real purpose here is we want everyone to walk away and understand why some piping systems vibrate when they're in service. We also want everyone to walk away understanding some common causes of that, and how to readily recognize them, whether you recognize them while they're actually occurring in the field, or you recognize them when you're proposing a new project or going to develop a new project in a particular phase. And we want to explain some of the reasons why it's important to mitigate and manage those piping system vibrations. And we would also like to highlight how, what could CDI do to help, reduce likelihood of failures resulting from these vibrations in piping systems. So the objective here is everyone walk out of here being able to answer these questions. So first thing I want to talk about briefly is static and dynamic pipe loads. Because it's really obviously dynamic pipe loads are what is our driver for dynamic stresses. So, but I did want to give a background here to some static loads, so we can easily distinguish between what is and isn't. So, a static load is the influence the pipe system uniformly, such as weight, pressure, and they normally would influence it gradually, such as thermal expansion. These loads, we normally would not care about a time component with these, because it's would be ignored, and also it has little to no effect on the system. Some examples of static loads would be weight, pressure, thermal expansion. Uniform loads such as ice is a good uniform load. It's occasional, but it is a good uniform load. Wind loads, we would treat wind loads as a static load, and analyze a piping system. Now, dynamic loads, are characterized by having a frequency and an amplitude. These loads are applied rapidly to a piping system. And these loads are where we need to consider the time component of how that load is being applied. Time's going to play an important role here in the nature and the magnitude of the resulting stresses from that load. And we'll talk later about a pressure surge, and you'll see where time really plays a part in that. And some examples of these are, water hammer, pressure surge, be the same thing, steam turbine trip, a PSV discharge, and then of course we're going to talk about some harmonic vibrations as well. So with that being said, we're going to look at a couple other things. Many of us understand what natural frequency is, but we need to understand that every piping system has a natural frequency. And we also want to understand this frequency is normally measured in hertz, and it's normally some cycles per time. In hertz, of course, it'd be cycles per second. So we want to talk about, this is one of our first questions: why do piping systems vibrate in service? In service, there's steady state loads on the piping system, which are considered to be balanced. And then in service, dynamic loads that would tend to be unbalanced. And the unbalanced forces tend to actually create this vibration. And so in this diagram you're looking here, if P3 and rho V3, that force generated by that is greater than P2 rho V2, then of course you would have some force driving this thing to move. So I really wanted everyone to understand why they vibrate, and they truly vibrate due to unbalanced forces within the piping. So what are some common causes for piping vibration, and how do we recognize them? We're going to take a minute in the next few slides, and we're going to kind of talk through these briefly. Mechanical excitation, flow-induced turbulence, some pulsation, high-frequency acoustic excitation, cavitation, flashing, and we're going to talk also about some surge and momentum changes as well. So I picked this picture because I thought it was a really nice picture of being able to illustrate a mechanical excitation that has absolutely nothing to do with a piece of equipment in a plant. But mechanical excitation is normally a result of connecting a piece of equipment, such as a reciprocating pump, reciprocating compressor, to some piping system, and then the piping system is actually excited by it from that movement and amplitude of that piece of equipment, and you end up with this harmonic wave you see here. In this particular example, I wanted to show here the man here is actually exciting this rope with a frequency. His hand goes up and down every so at some point in time, and he's also with some amplitude. It goes up so far and it goes down so far. So I thought it was a good real world example of showing how mechanical excitation could be shown in other things. So obviously, if this rope was much stiffer, these displacements of this rope would be much less. And another good thing that this picture demonstrates is how this excitation and this harmonic dissipates toward the anchor point. If you notice at the anchor point, it's anchored there and it pretty much doesn't exist. So I wanted to go through this. I thought it was a good way to illustrate that. So another one we're going to talk about is flow-induced turbulence. Generating a straight run piping by a turbulent layer at the walls with the severity dependent on the flow regime as defined by Reynolds number. Most of us are engineers and we understand what a Reynolds number is. I'm not going to get too deep into exactly the correlation between flow induced vibration and flow induced turbulence with a correlation to an actual Reynolds number. That would be a whole nother deeper subject. But in most cases, the dominant sources of this turbulence, they really manifest themselves around such as bends and tees and reducers and partially closed valves. We're going to talk more about that in the next few minutes as well. Pulsation is reciprocating equipment, anything positive displacement, pumps, compressors, and even some centrifugal machines also deal with pulsation as well. And then, of course, dead leg piping is something that I've seen often where we'll have a main line and you have another line you use very infrequently. That basically, for all practical purposes, is a dead leg piece of piping because it's not in service all the time, but yet it's causing some vibration issues of the main line. And then, of course, pulsation occurring over thermal wells, which y'all are most all familiar with, but it's purely something that protrudes into the inner wall of the piping that the flow has to go around. And so the high frequency acoustical vibration is normally associated with control valves, orifice plates. Most of the failures I've ever seen associated with this were dealing with either PSVs, downstream of PSVs, downstream of blowdown valves, downstream of control valves, and most of those failures are normally about a yard or a meter downstream of the actual device, and it would normally result in a fatigue cracking issue in those pipe walls in that area. The one thing I want to mention here is with this, the frequency is very high. The amplitude is normally fairly low. And so it's a lot of cycles with a smaller amplitude is really what this is represented by. So I want to talk about cavitation in a minute. I mean, cavitation is a dynamic process of bubbles forming in a liquid. So these bubbles form when they go through a contraction. And then after the contraction, if y'all recall, the pressure's trying to reestablish itself downstream of this, such as a flow orifice or a valve or whatever the case may be. Well, cavitation is actually those bubbles that are formed actually collapsing as they're colliding with the walls of the piping. I have a little diagram down here at the bottom that's a pretty good illustration because we're going to look at flashing in a moment as well. We're setting up a normal control valve or a successful control valve. We would look something like this, and we would never want to dip down below the vapor pressure. But in cavitation, if you notice here, the pressure drop dips down below vapor pressure and then recovers back above vapor pressure. So the bubbles all collapse out. If you notice flashing here, flashing is actually where you dip the pressure below vapor pressure and then the bubbles really don't necessarily recover back out and collapse. And you end up with a two-phase flow regime downstream. So we'll look at this here, and this is a little more blown up illustration of that. The pressure drop going across the orifice, and then of course the recovery is it does not really get back to above vapor pressure, and you end up with a mixture of two-phase flow. Now, way down the pipe, it could possibly recover back above the vapor pressure. But when this occurs, vibration excitation basically sends shock waves down the pipe and that propagate from that origin. And it actually, results in an imbalance that's caused by this liquid vapor phases and two-phase flow. Everyone's probably fairly familiar with it. It can be kind of tricky. So want to talk a minute about surge and momentum changes. Most of us have dealt with these in more than one place, but surge, in simply put terms, it's I have a long piece of pipe, and at the end of that, and I'm flowing a mass down this pipe, and then at the end of that, we're gonna close a valve, and of course, from that closure, all the momentum of that flow wants to keep going. And that's, in a very layman definition, that is what we would refer to as pressure surge. I have an example, a really brief couple slide example. I'm going to show you in a minute how to deal with that. And relief valve discharge, most all of our plants and clients are familiar with that. As this relief valve would release, and we just, for this illustration, shows it turning up here. There's quite a bit of force pushed back down from that exit velocity of that flow, that discharge. So steam turbine trip, we touched on that a moment ago. And this tends to create a water hammer effect in a steam inlet line. So it's somewhat synonymous to this, but a little different product, a little different flow problem. Then we have slug flow, and slug flow is really created by operations of piping system with two-phase flow in an undesirable flow regime. In two-phase flow, there's a lot of different flow regimes you could try to operate in. Dispersed, there's a flow regime where slug flow will actually form and occur. And so typically we would resolve this by the change of pipe sizes, and maybe we want to reduce the pipe size, speed the flow up to get us out of that slug flow regime. Or maybe we would like to change the process conditions and put more gas in there, less gas in there. But often that's solved through one of those means. So why is it important to mitigate and manage piping systems vibrations? Well, fatigue cracking is probably going to lead the race there. I mean, fatigue cracking, based on what research I've done, has been in the past a major contributor to up to 20+% in major industrial accidents. I'd actually pulled this out of a reference out of the Energy Institute guideline that we're going to talk more about in a moment. But so about 1/5 of our major industrial plant accidents deal with some form of fatigue cracking in piping systems. So that's a lot. So that's why we want to do something about it. That's why it's important that we manage this. Fatigue life can be really tricky in the sense that a fatigue life for a component can be very short and it can be very long. So it's really highly dependent on the combination of the amplitude and the frequency of the vibration. So another item here that I wanted to mention was fretting. And often you see piping that's setting directly onto steel, like this picture I have here at the bottom. And if you see a piping setting on a steel out in your plant, and you notice that the piping is actually working itself back and forth as a movement, then you also know that there's some fretting going on here. And given enough time, it will actually eventually wear a hole in it. So, when you see that a piece of piping is physically moving back and forth on a support, it could be an area that you'd want to look more closely at. So, what can we do to reduce the likelihood of failure resulting from piping system vibrations? So, we want to go over some rules of thumb. I'm going to go over briefly some Energy Institute guidelines. Energy Institute published this guideline back as a joint effort around the final one being around 2008. It was actually a joint effort between many, many different companies, and it is a great tool for mitigating fatigue failure in piping. We're going to talk a little bit about how we can use Caesar and how Caesar can also be used in conjunction with an EIG guideline. And we're also going to talk about how we can use Caesar also to take an existing piping system, for instance, and do a cumulative fatigue analysis on that system and give you some kind of idea of what kind of predicted replacement life you have. According to this analysis, your piping is, probably due to be changed 5 years from now. So this can be really good for helping, plants and owners figure out exactly when they may actually want to start replacing some piping due to the end of the life fatigue. And we're going to talk briefly about some other tools and analysis as well, some CFD. We use Siemens Star CCM Plus, and we have an Autodesk CFD, and we also and we're going to talk briefly a little bit about FEA as well. We use Abacus FEA and some Pollen Research Group Nozzle Pro FE pipe, some of the tools we use. So some common rules of thumb. And honestly, these are probably some of the best things that we can get out of this and walk away with is us, our piping designers, the project managers, understanding these few things right here really help a lot. So we want to minimize bends, tees, and dead legs. We really don't want to put any more bends and tees and dead legs in there than we have to. One, bends and tees and dead legs cost money. Costs money to weld it in, and it also causes other problems with the piping down through its course of life. We definitely want to avoid concentrated weight at pipe midspans you can look at a good sized midspan and you need to put a shutoff valve in that midspan between these two supports. You don't want to go out into the middle of that pipe midspan and put that valve out there. You want to locate that valve toward one of the supports or the other. We can provide clamps, guides, anchors, to reduce flexibility and limit some of this movement and instability as well. So we want to ensure this is actually pretty important too. We want to keep the stiffnesses of these structural supports, about twice the stiffnesses of the pipe span or greater. We want to avoid resonance frequencies. We'll look at that a little more in a moment. And recognize that it's easier and less costly to simply restrain a vibration than to analyze the actual pipe stresses resulting from it. With the right restraints and supports, it is often the most economical way to approach this. So in some cases, we may need to look at actually modifying our process conditions and to avoid, dynamic related issues. And also at times we add pulsation dampeners, expansion tanks, vibration snubbers on, dampeners again that go on piping systems. So there are other mitigations there that we can add through additional design as well. So I want to talk a little bit about Energy Institute guidelines. This is the avoidance of vibration-induced fatigue failure in process pipe work. This EIG guideline is a formal methodology that was developed to minimize the risk of this vibration-induced fatigue. It's actually a really great guideline. I would encourage everyone to get them a PDF copy of it, take a look at it. I know at first view of it, it looks daunting. And because there's so many, go here, do this, go here, do that. Personally, the first time I ever looked at it, I was like, wow, this is a lot. But after a while, you kind of get a feel for what it's doing, and it tends to become second nature to you. So these guidelines can be used in a lot of ways. They can be used and applied to a new design, an existing design, a change that you may want to an existing design, and also the guidelines are really useful in solving any type of identified issue that you may have that's in an operating system today. You've got a plant and this piping seems to be moving with some frequency and amplitude from your visual observation, and you think, yeah, well, I wonder how long that pipe's going to shake before it's going to break. And so this guideline can be really useful in evaluating that as well. So at CDI here, we've developed a lot of evaluation tools based on these guidelines, and to really actually help us do these guideline assessments and likelihood of failure assessments in a timely and very cost efficient manner. So I wanted to point that out as well. So for the sake of an example, we're going to do a simple go through. And this is really how simple these guidelines can be. It obviously, when it's a different fluid, it's different other things. Obviously, it's a little different roadmap. But for this example, I picked a gas and it's single phase. It's all gas. So step one here, we're going to calculate a mass momentum number, which is actually the actual density times the velocity squared, which is purely just mass momentum, if y'all recall from school, rho v squared. So when we get this number in those guidelines, they have some mass momentum numbers. They say, well, if it's below this number, the likelihood classification is low, and I probably wouldn't even look at it anymore. Or when it's in this number, it's in a medium classification, you may want to go and do this, and this. And so the guideline gives you a roadmap here to follow. To get a mass momentum number is pretty straightforward. So let's say here we want to proceed. So next we're going to calculate this fluid viscosity factor. Really, the only major special thing about this is that kinematic viscosity number for the gas. It's a function of the kinematic viscosity of the gas. And then we're going to actually go determine a support arrangement. And I know that seems kind of odd that we're going to pick a support arrangement, but for each one of these different ranges of natural frequencies that you anticipate your piping to have, it would corresponds with what they have lumped into a major area. And then of course there's some span length calculation to go here, which are based on basic parameters. And that kind of defines how long, if I want this to be medium stiff, it should fall into this span length. And I would anticipate a frequency of around 7 hertz. So we would normally pick a span length, or we would take Caesar here and we would know what this particular piece of pipe frequency is. So if we knew what the frequency was, then we could come in here and we know what our stiffness is from that way. So there's more than one way to go there. And I wanted to kind of throw in there how we use Caesar Dynamic Modeler there. And so once we do that, we calculate the flow induced vibration factor. And this is all out of the EIG guideline. It's not a horribly complicated equation. It's alpha, and then there's a D outside over T, and it's raised to this beta factor. So equations are fairly straightforward, not super complicated. So we get to this, and then we calculate this likelihood of failure number. Understand, this is not saying, well, if I got an LOF, it's 0.3, does that mean that I have a 30% probability in failure? No, that's not what this number tells you. What this number tells you is, based on historical data, with this LOF number of less than 0.3, you would have a very low likelihood of ever having a fatigue failure problem with that particular line. So, and it also gives some guidance on maybe some visual inspection you would do as well. So once you calculate this, which you see this is no more than rho v squared over FV times FVF, which I just went through a moment ago. And then, of course, if these likelihood of failure numbers increase, then the guideline actually tells you that you may want to do a small bore connection assessment. And this visual inspection, you want to make sure all your welds are smooth, you don't have sharp edges. But when you get down where it gets where it's at 0.5 or greater, then they start actually saying you might want to look at redesigning the piping and supports. So this is, in a nutshell, what the guideline does. It's pretty straightforward. And I know I've just touched on a drop of it, and when I'm sure some of y'all go look at it and find, well, and there's a lot in here. So, and I've only touched on one particular type, flow-induced turbulence. So I want to go into Caesar 2 dynamic analysis, and I'm probably running behind on time, but we use it, and mainly I pointed out earlier, we use this in several ways. One, we use it to get natural frequencies of some complex piping systems. And we also would use it to predict the dynamic stresses as well that we're seeing on a particular set of piping. And then we can use Caesar and set in a set of operating conditions and do fatigue life, cumulative fatigue life damage to a piping system. Doesn't have to be a new system. It could be an existing system. If you have a system that's been vibrating for years and you're thinking, well, I wonder if that's really a problem, then by all means, it can be looked at and you can get an idea of what your fatigue life remaining is on that, rather than just not knowing anything. So some other tools that we often use, and I wanted to give you a real brief here. We use the CFD, and one of the things that we've successfully done that's really I find kind of amazing is perform co-simulations using STAR CCM and actually do a CFD model inside of an Abacus FEA model and get actual forces and stresses all within one model where we are actually doing the computational fluid dynamics at the same time and doing this all within the same solver. So this is actually a fairly complex analysis, but we've had clients where they have a flare line that they're having two-phase flow in, and they don't really have great data on it, but they kind of know what's going in there, and we can put that in the model like this, and we can run that and get some ideas of what's going on in there with respect to forces and stresses. So I'll do a real quick pressure case here on a surge one. So we have a 10-inch line. It's carrying some fluid to a loading dock. It's a couple thousand feet away. It's running 1,000 gallons a minute. And we want a valve at the end. Let's say we have some regulatory project where we're putting in some breakaway valves. We're loading on the Mississippi River, and we're going to install, and I'm kind of giving y'all some background on stuff we've done. We're going to install these breakaway valves, so when the ship were to pull away, it just pulls the hose away from the dock, and the valve shuts itself immediately behind that. So in this particular case, we want to talk about what kind of force would we see down on this other end of the pipe. So real simple calc, most anyone could do. You could calculate a really rough surge pressure just from the density of the liquid and the speed of sound through the fluid, and then a change in velocity. So that's not a huge effort to calculate that. You can say, well, I'm expecting to see a pressure surge of about 233 psi. So then, of course, from a really simple calc, you can go, what kind of force would that be on the piping? So really, it boils down to, okay, it's 233, and we have so many square inches, and which is really just the internal diameter, cross-sectional area of the piping. And lo and behold, well, when that happens, we're going to have a force that hits into this pipe at 18,000 pounds. Most times that really doesn't get managed by putting in more supports. Most of the time that gets managed by some pulsation expansion type tanks on the other end. But this is really a simple calc that anyone could do in just a few seconds. It's not difficult. Another one I wanted to go through, and this is a job that we did as well. And there's a few things that I thought were really good to show here. One of the things we did this with Caesar 2 dynamic modeler, by the way. And if you notice in here, we have a mode shape 1 and we have a mode shape 2, which has a natural frequency of about 1.6 hertz. And if you notice when I run this animation, you're going to see that this mode shape and this mode shape are both the column. One of them is in this plane and one of them is the column in this plane. And if you notice, our closest connecting pipe mode shape is around 3 hertz here at mode 3. And one of the things that we would normally make sure of that we do, we want enough separation between the natural frequency of the column itself or any piece of equipment versus our piping. And here, if you notice, we have almost a 2x separation here. So I want to run this and let everyone see what I'm talking about. So that's actually the column in one direction, one plane. And then, of course, this is the column in the other plane. If you notice, this is that mode shape at the very bottom down there where the horizontal piece is. This is the mode shape of actually, that's a 3-inch. It ties into it. It's associated with it. And of course, that's actually up around 5 hertz. Now, did we see an issue with the column influencing the 5 hertz plus? No. So that's really what I want to show you here, that we use Caesar dynamically to confirm that we're not going to have an excitation issue from the actual equipment it's connected to. Let's see. That's pretty much what I had. And I think we were going to do some questions and comments. I think out of 11:44, so I haven't burned all the time. Would we like to take a couple of questions?
All right, thanks, Barry. Clearly, this is a really important subject, so thank you for going over all of that. We will take a few minutes for questions. You can put them in the chat box there. And I know there's one, well, it looks like we have one right off the bat here. Barry, per Energy Institute guidelines, I know you did touch on that briefly, exactly what parameters of the piping system are needed to determine that likelihood of failure for the piping system?
So good question. Pretty simple. your basic piping parameters. You're going to know diameter, wall thickness, corrosion allowance, those type of things. You're going to need to know the flow, and you're going to need to know parameters around that flow. Density, is it single phase liquid, two phase? So you're going to those basic inputs will actually get you to a likelihood of failure analysis being done. Another thing that you may want to understand when you're doing that as well would be what exactly frequencies am I dealing with? Is it, if it's an as-built already in the field, you may actually want to model that and get the natural frequencies of the piping you're dealing with. If it's a new design, you may want to declare you a natural frequency that you want to design to. So that's kind of a proactive versus reactive mode there.
Okay. Barry, how can you determine what's an acceptable closing time for a valve to prevent excessive pressure surge?
The valve closure time is evaluated with respect to the wave cycle time of the system. A wave cycle time is the product of the total length of the pipe and the speed of sound in that particular fluid. So it's a time that it takes the wave to make a complete cycle. That's from the source to the valve and back to the source. So that sort of defines the closing time. If you set your valve closure time, let's say you calculated that and it was, I don't know, 3 seconds. You'd want, if you set your valve closure time to close in 10 seconds, you would never really see any issue with surge. So that's a good check when you're doing something like that, is to kind of understand that, what that is, and then, well, yeah, we can set this valve to close in 10 seconds and we don't have to deal with all this surge, right?
Okay. Thanks, Barry. One more looks like so far. How can CDI account for cumulative fatigue damage in piping systems?
Yeah, I kind of touched on that a minute ago, but Caesar has a great way of managing that. And then, of course, within Caesar, there's a multiple different approaches to doing that as well that are actually part of Caesar. And so the calculation in Caesar really, it sums the fatigue damage over multiple load cases, but it does it in a weighted process where fatigue stresses from each load case are weighted based on the load case's number of cycles versus an actual allowed cycles. So you're really telling it that I want to sum up a damage based on this many cycles. And that's really what you're telling Caesar to do. Great tool to do that with.
All right, great. Thank you. And yes, we will share these slides after the webinar today. We'll share them with everybody who joined us. So thanks for asking that question. Does anybody else have any other questions for Barry before we end for today? All right, looks like we have one here regarding Caesar model analysis, which you showed. Do you consider the stiffness factor for friction? And if so, which valve are you using?
We do, in that particular model that you looked at, we did actually have consideration for friction in there. Yes. And however, like up at the top support there, we considered friction, but friction there become somewhat a moot point because we also put guides there as well. But yeah, we don't normally we would consider friction factors, if that answers your question.
Okay. Barry, I don't see any other questions. Oh, as per Energy Institute guidelines, how can one get it? They've tried to get it and hasn't been successful.
I'm going to take that one offline, and I can help. But Energy Institute, this avoidance of vibration, is really a public domain document. So send me an email. You have my contact stuff on the screen right there. Send me an email, and I'll be glad to help you with that.
Okay. All right. I guess that will be it. Laura, I'm going to pass it over to you to do our final wrap up.
Great. Thank you, everyone. We appreciate you being here. We'll upload this webinar on our YouTube channel. We'll also email all of y'all the slide deck for those of you who joined us today. If you would like a PDH certificate for your attendance, please email me, Laura, LAURA.LeBlanc, LEBLANC, @cdicorp.com. Thanks again, and we will see everyone next time. Happy holidays.
Thank you.